The classic econometric model for sample selection is the so-called Heckman selection model. This model allows both for selection on observables and on unobservables. In other words, it allows people who attend Oxford to differ from those who do not attend, both in ways that we can observe from their application files and in ways that we cannot. To accomplish this impressive feat, the Heckman selection model relies on fairly strong parametric assumptions. These assumptions can be weakened to a certain extent, but not perhaps as much as we might like. Selection on observables is fundamentally a very hard problem. The Heckman selection model is based on the following two equations. The first is called the outcome equation, and the second is called the participation equation. The outcome of interest, y1, is only observed for people who participate. In other words, people for whom y2 is equal to 1. Our goal is to learn the parameter beta 1 that relates observed characteristics x1 to the outcome of interest y1, despite the fact that we only observe y1 for a selected sample. In the admissions example, exam results are only available for students who complete the first year of the MPhil. The vector x with no subscript contains all the information that we can observe about candidates when they apply to the MPhil. The first component of x, which is labeled x1, contains those covariates that enter both the participation and the outcome equations, while the second component, x2, contains the covariates that enter only the participation equation. It's possible that x2 is empty. In this case, all the covariates enter both the participation and outcome equations. When x2 is not empty, we say that there is an exclusion restriction. In other words, there's at least one covariant that matters for participation, but not outcomes. We can think of this as analogous to an instrumental variable. As we'll discuss further in a few minutes, exclusion restrictions aren't strictly required to apply the Heckman selection model, but if available, they're extremely helpful. Both the participation and outcome equations are linear in parameters and depend on the observed covariates x. But thus far, we've said nothing about the unobserved error terms, u1 and v2. Selection on observables enters through x. Application files of people who attend Oxford are different from those of people who do not attend in ways that matter for first-year MPhil grades. The observables x1, which are a subset of x, enter both the selection and outcome equations, and this is where we can obtain selection on observables. To allow selection on unobservables, we need to allow an unobserved variable to enter both equations. This is equivalent to allowing u1 and v2 to be statistically dependent, in that knowing something about v2, which affects participation, tells us something about u1, which affects outcome. The assumptions B, C, and D on the slide concern these unobserved errors. Turning our attention first to B. B is essentially an exogeneity condition. Its first part is not restrictive. It merely says that the expectation of u1 and v2 are both 0. This is satisfied automatically if we include an intercept in both the participation and outcome equations. Say, if we just define the first element of x1 to be equal to 1. In contrast, the second part of assumption B is indeed restrictive, and it's somewhat stronger than the more standard exogeneity assumption that we'd make, say, in a linear regression model. This is because we assume that u1 and v2 are jointly independent of x, rather than, say, just uncorrelated with x. Notice that the participation equation is, in fact, a binary outcome model, much like the ones that we studied in an earlier lecture. Assumption C on this slide says that it's, in fact, a probit model, because the error v2 is assumed to be standard normal. Assumption D maintains that the conditional mean function of u1, namely the error term that enters the outcome equation, is a linear function of v2 with an unknown parameter, gamma 1, that we will somehow need to estimate. This slope parameter controls the nature and extent of sample selection bias. If gamma 1 is positive, then among candidates with equally strong applications, those who choose to attend Oxford tend to perform better on exams than those who do not choose to attend. The larger the value of gamma, the stronger the effect. This assumption D can be relaxed to allow for more general forms of dependence between U1 and V2, and in fact, you will consider just such an extension in your problem set. Now, depending on which references you consult, you may see my assumptions C and D replaced by the single assumption that U1 and V2 are jointly normally distributed. This joint normality assumption implies the assumptions that I use here, but it is strictly stronger in that I will not require that U1, the error term in the outcome equation, actually follows a normal distribution. Under the assumptions from the previous slide, it turns out that beta 1 can be identified from a pair of straightforward regressions, even though we only observe data for the selected sample. The argument relies on two key lemmas. We'll prove these in later videos, and for the moment we'll content ourselves with understanding what these results mean and why, in combination, they allow us to solve the sample selection problem. The first lemma says that the expected value of y1, and recall that that's our outcome of interest, so in the MPhil example, that's first-year MPhil exam results, the expected value of y1, conditional on x, and the fact that y2 equals 1. So this is the conditional mean of MPhil exam results, given characteristics that we observe, and given that someone was admitted to and chose to attend Oxford. This is equal to x1 prime beta 1 plus gamma 1 times the expected value of v2 given x and y2 equals 1. Now recall that v2 is the error term in the participation equation, and once again we're calculating a conditional mean given what we can observe, x, and the fact that y2 is equal to 1. So both of the two conditional expectations in this lemma are for the selected sample, for the people who choose to attend Oxford. So what does this lemma mean, and why is it important? First of all, let's be clear about what we know and what we don't. X is observed, and recall that X breaks down into two components. X1 contains the covariates that affect the outcome y1, and X2 contains the additional covariates that, besides X1, enter the participation equation. Now, beta 1 and gamma 1 are unknown constants. These are things that we would like to be able to estimate. However, the expected value of v2 given x and y2 equals 1 is actually a function. This is a function of x. It maps the regressor vector x to a scalar. Let's just call this function h of x. If it were known, then we could simply define w equals h of x and treat this as an additional regressor, in which case the right-hand side of the lemma would be x1 prime beta 1 plus gamma 1 w. And since the lemma says that the expected value of y1 given x and y2 equals 1 only depends on the covariates x through x1 and this thing we've just defined to be w, we have two very important consequences. First of all, it shows that regressing y1 on x1 and w for the subset of individuals with y2 equals 1, in other words, for the selected sample, would suffice to identify both beta 1 and gamma 1. This consequence is so important that it bears repeating. Regressing y1 on x1 and this w random variable that I've just defined using data for the selected sample allows us to identify the parameter beta 1 that governs the relationship between y1 and x1 in the whole population. In other words, we can learn the effect of education on wage offers in the population as a whole, despite observing wages only for people who are employed. Now, to be able to do this, we need a way of calculating this additional regressor w that I defined as h of x, where h is this conditional mean function of v2 given x and y2 equals 1. Second, this result shows, as I asserted earlier in the video, without proof, that any bias arising from sample selection does indeed come from dependence between the errors in the participation and outcome equations. So if gamma 1 were 0, which would imply that the conditional mean of u1 given v2 was just the same as the mean of u1, which is 0 by assumption, then there would be no sample selection bias. And in this case, we would have the expected value of y1 given x and y2 equals 1 equals x1 prime beta, which would mean that in the case in which gamma 1 is 0, a regression of y1 on x1 only, using the subset of individuals who have y2 equals 1, namely the selected sample, would identify beta 1. So that's the first lemma. Now, to be able to use that lemma, we need to figure out which function this h actually is. And that is where lemma 2 comes in. Lemma 2 shows us that the expected value of v2 given x and the fact that y2 equals 1 is equal to phi of x prime delta 2 divided by capital Phi of x prime delta 2, where lowercase phi is the density function of a standard normal random variable, and uppercase phi is the associated cumulative distribution function. So this shows us that that function h of x described above is equal to the so-called inverse Mills ratio, which is a name for this particular ratio of a normal density to a normal CDF, evaluated at x prime delta 2. That is the linear predictor from the participation equation. Just one word of notation, I am calling the inverse Mills ratio lambda, and I also used lambda in a previous lecture to denote the density function of a standard logistic random variable. Just to avoid any confusion, I want to be clear that these are not the same thing, but I'm using the notation lambda here because that is the most common notation for the inverse Mills ratio. So lemma 2 shows us how to construct the function h of x that we needed to know in order to run the regression I mentioned above under lemma 1. We just need to figure out the value of the parameter delta 2. As soon as we have this, then we know exactly how to calculate that additional regressor that I mentioned before, w. So how can we learn delta 2? Well, this part is easy. I'm not even going to call it a lemma because it's something we've already seen in an earlier lecture. We know that the participation equation is a probit regression. It also has the property that we observe the outcome of the participation equation for everyone in our sample. In other words, among everyone who applied to Oxford, we know precisely who was accepted and attended. Because of this, we don't have to worry about sample selection. We have a representative sample from the population for the participation equation. So to estimate delta 2, we can simply run a probit regression for the participation equation. The logic of the preceding slide gives rise to what is called the Heckman two-step estimator, also known as Heckit. Again, we assume that the researcher observes y2 and x, a random sample of size n from the population, but only observes y1 for people with y2 equals 1. In the first step, we estimate delta 2 using the full sample. To do this, we run probit on the participation equation. In other words, the model is the probability that y2 equals 1 given x equals capital phi of x prime delta 2, and we calculate the maximum likelihood estimator delta 2 hat of delta 2. Using this MLE, we construct lambda hat I. This is that regressor that I was calling W before, that we construct by evaluating the inverse Mills ratio, the function lambda, at individual i's covariates, xi, using our maximum likelihood estimator, delta 2 hat, to stand in for the true unknown parameter vector of the participation equation. In the second step, we simply plug in this lambda I hat for that missing regressor, wi. So using the observations for which yi1 is observed, namely using the selected sample, in the second step, we regress y1 on x1 and the lambda hat that we constructed in the first step, and this regression is simply by OLS. The resulting estimates, beta 1 hat and gamma 1 hat, give us what we're after. Namely, beta 1 hat is an estimator of the relationship between x1 and y1 in the whole population, not just the selected population, and gamma 1 hat is an estimator of gamma 1, which tells us the nature and extent of the sample selection problem. So what exactly is going on here? How does this Heckit approach solve the sample selection problem? Fundamentally, the problem of sample selection is that if we regress y1 on x1 for the selected sample, there is an omitted variable. Under the Heckit assumptions, this omitted variable, which I called w 2 slides back, turns out to be exactly equal to lambda of x prime delta 2. Hence, a regression of y1 on x1 and the omitted variable is a correctly specified regression. If you've been paying very close attention, you may have noticed something slightly odd. In the second step regression from the Heckit procedure, x1 makes a double appearance. It appears first in its own right as one of the regressors, and second as a constituent of x inside of the inverse Mills ratio function lambda. So what exactly is going on here? How can the same regressor vector appear twice on the right-hand side of a regression? Well, there are two possibilities. The first and simplest is when x contains some variable that is not in x1. This is when we have an exclusion restriction. In other words, when x2 is not empty. In this case, there's clearly no problem because x prime delta will not be perfectly collinear with x1, and so whatever this lambda function is, even if it were a linear function, we would not have a problem of perfect multicollinearity in our second step regression. However, as I mentioned before, it's not strictly necessary when applying the Heckit approach that we have any exclusion restrictions. You can use this method when there are no elements of x that are not contained in x1. This situation, the one in which there is no exclusion restriction, is more challenging. If lambda were a linear function, we'd be dead in the water in this case, because then x1 and lambda of x1 prime delta 2 hat would be perfectly multicollinear, so there'd be no way to separately identify the coefficients on each of them. However, the inverse Mills ratio function, namely lambda c is equal to little phi of c divided by capital Phi of c is in fact a nonlinear function, as we see at right, plotted for a range from -4 to 4. Because of this nonlinearity, lambda of x1 prime delta 2 will not be perfectly collinear with x1. However, identification without an exclusion restriction is typically viewed as much less credible, because here all of our identifying information comes from the nonlinear shape of the inverse Mills ratio. So people are typically concerned that we are making too much of our model assumptions in such a setting, and as a consequence, may not be so inclined to trust the results. A more pedestrian but no less important problem that arises when we lack an exclusion restriction is that over relatively wide ranges of c, the function lambda of c, depicted at right, is quite close to linear. So while x1 and lambda of x1 prime delta 2 may not be perfectly collinear, they might be nearly perfectly collinear, in which case the estimates that we obtain from the Heckman procedure could be extremely noisy. While we won't go into the proof here, it turns out that under our assumptions and some additional regularity conditions, the Heckman estimators are consistent for the true population parameters that they estimate, and asymptotically normal as the sample size goes to infinity. There is a slight wrinkle here, namely that the Heckman two-step approach requires us to carefully calculate the asymptotic variance omega. In particular, the usual OLS standard errors that you obtain from the second step regression will be incorrect because they fail to account for the fact that this additional regressor that we introduce in the second step is actually estimated from data in the first step. In practice, this isn't something that you have to worry about. I just suggest using a canned Heckman routine rather than trying to program your own.